Hello all, welcome to the fifth module of this course, Digital Circuits and Systems. So, I want to give a quick summary of this notion of min terms and max terms. So, we have the familiar truth table representation, we have 0 0 0 to 1 1 1 and they correspond to row numbers 0 to 7. So, I mentioned that the small case m is used for min terms and uppercase M is used for max terms, and the subscript is indicative of what is the term that you are talking about. So, for a min term, if you say 0, it is actually 3 bits 0 0 0, and what it means is x1 is 0, x2 is 0, x3 is 0 and so on. For max terms, the interpretation is if you see a 0 0 0, then x1 is in the uncomplemented form, or x2 in the uncomplemented form, or x3 in the uncomplemented form. So, one thing that you can notice is if you look at the small case m naught and the capital case m naught, you will see that the term here is actually the logical complement of the term here. So, use De Morgan's theorem, you have x1 or x2 or x3. So, the complement of the sums is product of the complements. So, you can see that, repeat. So, I want to give a quick summary of min terms and max terms that we did in the last module. What we have is various row numbers here and their integer and their binary representation here. I mentioned that min terms we will use this small case m, and for max terms we use uppercase M. So, and when we say m0, we are talking about m x1 in the 0th row, m in the 0th row where everything is 0, and the interpretation is x1 is complemented, x2 is complemented and x3 is complemented. So, that is what you see here. The max term interpretation of that is x1 is uncomplemented or x2 uncomplemented or x3 uncomplemented. So, one thing you can notice is that this m and this m are actually logical complements of each other. So, use De Morgan's theorem, you see that you take this and you complement it, you will get this. So, complement of the sum here would be the product of the complements here. So, this is something that is interesting, it makes simplification easy. So, we will see how. So, one thing you can notice is if you generalize this setup, the capital M subscript I is the same as small m subscript I complement. So, the term that you have min term, the ith min term, you take the complement of that gives you the ith max term. And similarly, if you take the complement of the ith max term, that gives you the ith min term. So, if you have something which is complement of each other, then the direction, so it goes in both directions. Then what that tells us essentially is if you have this, then if you are given a, let us say a sum of product expression like this, so you have sum of 1, 4 and 7, and 1, 4 and 7 are min terms because we said it is sum of products. So, it is m1, m4 and m7, the logical OR of those. What this gives us as a powerful tool is that if you are given sum of products, you can write the product of sums really quickly. So, the way to do that is you look at all the terms that are possible. So, you have terms, min terms starting from 0, 1, 2, 3, 4, 5, 6, 7 for a 3 variable function, but you are given only 3 of them here. So, 1, 4 and 7. So, the way to get the product of some expression is find out all the terms that are missing here and you put them down. So, you have 1, 4 and 7, you are missing 0, 2, 3, 5 and 6 in the range of values 0 to 7. So, you take all those terms and you take the max terms and add them together. So, the sum of 1, 4 and 7 is the product of max terms 0, 2, 3, 5 and 6. So, this is a very handy thing, it is a good thing to remember because sometimes getting the product of sum is easier than the sum of products or the other way around. If this is a complicated expression, you try and do this and convert back, or if you think that this is easier to do, you get this and convert to this. So, let us I am going to give you a few examples of how to do algebraic simplification. So, we are going to use several rules that I discussed so far, we will also try and write things in SOP form and POS form and so on. So, let us start with a fairly simple one. So, this expression f of x y z, it is given there and clearly it is not in any form. So, it is not product of sums, it is not sum of products either, and the example is asking you to simplify that into the sum of products form. So what we need is, we need terms which are all product terms and we want a logical OR between those. So this is not sum of product because you have a product, so x bar in and y plus z bar, and that kind of thing is not allowed in the sum of product form. So let us see how to simplify it. So the first thing you can do is, you can see that x bar here is ANDed with y or z bar, and there is also y that is ANDing from the other side. So if I take all these terms and expand it, so this is x bar here, y and z bar here, and this y here. This z bar is associated only with y, so you expand that. So it is fairly straightforward algebra here. Then now you bring x and y inside, so this y gets x bar and y, so that is x bar y y. So this z bar gets x bar and y, so that is x bar z bar y, and this is z bar y. And if you notice, there is y and y here, that is the same as y. So x bar y y is same as x bar y, then x bar z bar y we write it as it is, and let us say z bar y we write it as z bar y 1, because we see that z bar y is occurring in this term also, we write it as z bar y 1. If you simplify it further, this term remains as it is, and there is a z bar y which is common between these two, which means we can eliminate x bar. So essentially we get x bar y plus z bar y. So this is a valid sum of product form. So x bar y plus z bar y is a valid sum of product form. The same thing if you want to write it in product of sum form, in this expression at least it is fairly easy. All you have to do is, you can see that y is common between these two, so it is y into x bar plus z bar. That is actually a valid product of sum expression also. You can take this expression here that you got from SOP and you can quickly convert to POS for this example. So it is just x bar plus z bar into y, x bar plus z bar is a valid sum term and y is a valid sum term, so the product of those two is a valid POS. So let us move on to another example. We want to write something now in the canonical SOP form. So let us look at this one here, x bar y and z bar y is what we had in the previous example. So the first question is, I am asking you to do this in canonical SOP, and why is this not canonical SOP? So let us look at that. The left side we have three variables x, y and z, and in a canonical SOP we need all the variables to be in all the terms. So remember, this should be normal terms, which means we should have min terms that capture the same logic functionality on the right side. So we have f of x, y, z, this one does not have z term and this one does not have a x term in it. So this is a valid SOP, it is not a canonical SOP however. So if you want to convert something like this to a canonical SOP form, what you have to do is this. So this is missing a z, so I am going to introduce z bar plus z for this term. This term is missing a x, so I am going to introduce x plus x bar. So we already know that x plus x bar is 1 and z bar plus z is 1, so introducing that is not a mistake. So this line is taking something from here, whatever is missing we have written them out. Now this line is just expanding it, so you will take x bar y into z bar, so that is here, x bar y and z is that is here, then z bar y x, it is rearranged, the terms are rearranged because we know that logical AND is commutative, so this is x y z bar, and finally x bar y z bar, that is here. So now it looks like we have 4 terms and each of these terms have x, y and z in them. So the question is this canonical? So the quick answer to that is, it is not canonical because there are terms which are repeated in them. So if you notice, there is x bar y z bar and there is x bar y z bar even here. So this term is repeated twice, and a canonical SOP will have each product term appearing only once. So the next line actually changes that, we have x bar y z bar plus x bar y z bar, I am sorry, x bar y z plus x bar y z bar plus x y z bar. So we have this here, and this expression, the final step is we are arranging them in some order. So this order, so it is the same, this last line is the same as this line except that it is rearranged in some other order, the product terms are shuffled around. So if you look at this, this corresponds to the min term 0, 1, 1 or 3, this corresponds to the min term 0, 1, 0 or 2, and this corresponds to the min term 1, 1, 0 or 6. So there is 3, 2 and 6, we are rewriting that as 2, 3 and 6. So that is what we have here. You can write f of x y z as a canonical expression, you can write it as sigma of 2, 3, 6. So at this point I want you to think about this. If I gave you this expression and if I asked you for a canonical POS, you might have done this already. If I want a canonical POS at this form, all you have to do is take sigma of 2, 3, 6. We know that all the terms that are here, we remove those and put the rest of the terms in. So sigma of 2, 3, 6 in the canonical POS form is the same as pi of 0, 1, 4, 5 and 7. So I want you to go and think about it, and if possible even do that as an exercise. Let's look at another simple statement. We want to simplify something to the POS form. So in this case we are given something in the sum of product form and we want to convert that into a product of sum form. So we could go and take this route of taking the sum of product form and let us say write it in the canonical SOP and convert that back into the POS form. However, in this example specifically, it's the product of sum form turns out to be very simple. So we have xyz plus x bar y plus xyz bar. So xy is common between this term and this term. So you take that out, you get z plus z bar, and this is x bar y. So we know that z plus z bar is 1, so that gets killed. You have xy plus x bar y, and again y is common between these two terms. So you get y and 1, which is the same as y. So in this case, it turns out that the POS form is actually fairly simple, but this is only the POS form. This is not the canonical POS form. So if you want the canonical POS form, you have to do something else. So let's look at this example, simplified to SOP and POS forms. So let's say I have AB plus C into B plus C bar D. So this is clearly not in the SOP form nor in the POS form. So it's in neither of those. We want to convert that to both SOP and POS form. So if you are asked a question like this to convert to both SOP and POS forms, the first thing you have to do is get it in one form. So let's try and get it in the SOP form first. So you expand the product out. So AB into B is ABB, which is AB itself. Then you have AB into C bar D, that is ABC bar D. Then you have C into B, that is BC. Then you have C into C bar D, that is CC bar D. So we have these four terms. So this is a sum of product, but we can still simplify it because there are terms that are repeating. So if you want this in a slightly better way, then the first thing you can recognize is C bar D is 0, so you can remove that. So AB plus ABC bar D plus BC. So many times when you look at this, when the statement says simplify, we are asking for the most simplest form in which we can write it. So clearly if we leave it here, that is also a sum of product, but it is not the most simplified form. So if you leave it in this line, AB plus AB C bar D plus BC, again it is a valid sum of product, but we want to see if that is the simplest sum of product form in which we can write. It turns out it is not the case. So let us look at this one. AB is common between these two, so you can write it as AB into 1 plus C bar D plus BC. So at this point it is just AB plus BC. So AB plus BC, you cannot simplify it any further and still have an SOP form. So this is the simplest SOP form. It turns out getting the POS form from this is straightforward. B is common between these two, so B into A plus C. So remember, the question is not asking you to do canonical SOP and canonical POS. We are just asking write the simplified expressions for these sides. So in this case it turns out to be a straightforward process. So let us look at another example. We want to in this example we want to simplify to the POS form and expand it to the canonical POS form. So what that means is we first of all have to take this sum of product expression and see how to write it in the product of sum form. So this is not product of sums. We have two products and they are summed up. So we want to write it as instead as product of sums. So this is in SOP form. Let's see how to do that. So let's look at xy here and let's look at x bar z here. So clearly this is not in the form that we need right now. So the first step to do this is, So, if you have xy plus x bar z, one way to rewrite that is take this term here x bar z, logically OR it with the complete term product term here. So, it is xy plus x bar into xy plus z. So, what we have done is we have taken this term here and split it into two product terms. So, one can quickly argue why this should be correct. So, you have xy plus x bar into xy plus z. So, if you go back and look at it, so let us see if we can try and show if these two are the same. So, xy plus x bar into xy plus z. So, if I take these two terms, that gives me xy. If I take these two terms, that gives me xyz. If I take these two terms, that is x bar into xy, that is actually a 0 because x bar cancels with x, and the last two gives me x bar z. Right. So, this is the same as xy plus xyz plus x bar z, and if you do this, so xy is common between these two. So, I can rewrite it as xy plus x bar z, right. So, it is fairly easy here. So, what the thing that I am using is I am using this theorem, which is essentially a plus bc is the same as a plus b into a plus c. So, this is the theorem that I have used to expand to the first line. So, let us move on, let us see how to get this further. So, we have xy plus x bar, again this is a product term and that is a product term, but you have sum of products, we want to convert that to product of sums. We will use the same theorem as before. You have one term here and you have a product here, you want to remove it. So, I use the same thing, a plus bc is a plus b into a plus c. So, in this case it is x bar plus x and x bar plus y. So, you can see this x bar appears in these two terms and this x and y is split up as two different sums here, and this xy plus z we can write it as x plus z into y plus z. So, it is possible to do that. At this point, right, we have 4 product terms and so 4 sum terms which are ANDed with each other, and if you notice, so we have x bar plus y here. So, we have rearranged and written it here, then we have x plus z, we have it here, y plus z, we have it here, x plus x bar is just 1, we can ignore it. So, this is the POS form. So, if you go back and actually expand this product, you will see that it is the same as this one. If you take this, expand it and simplify it, you will eventually end up with this expression. So, this is the POS form. The question is this the canonical POS form? So, the quick answer is it is not, because again if you look at these terms here, so we have 3 sum terms, this term does not have a z, this term does not have a y, and this term does not have a x. So, we need to introduce those terms in each one of those, and the way we do that is just like what we did in the first step. So, we did this earlier. So, x bar plus y, this term is missing z and z bar, so we introduce a z bar here. This one is missing a y. To make it a valid canonical POS, we need y in this x plus z also. So, we write y bar, and for y plus z, x term is missing, so we write it as x bar. So, in this case x bar is 0, y bar is 0, z bar is 0. So, it is okay to logically OR a 0 because it is not going to change the value of this expression. Now, we will use the same trick. So, we have something of the form a, so we have something of the form a plus b and c, right. So, let us say this is my a, this is my b and this is my c, right. We have something of the form a plus bc, we are going to write it as a plus b into a plus c. So, that is what is in this line. So, x bar plus y plus z bar, we write it as z here and z bar there, then y bar gets split up as y here and y bar there, and x bar gets split up as x here and x bar there. So, it looks like we have 6 terms here. However, these 6 terms are there are some repetitions here, So this is not the canonical SOP because in canonical POS, it is not canonical POS because we have some terms which are repeating. If you remove the terms that are repeating, it turns out that this is the expression here. Now like I did earlier for sum of product, we may want to go and write this as the product of sum form using the pi notation. So let us take a minute to think about how to write this in the POS form. We have x plus y plus z. So this is in the uncomplemented, this is in the uncomplemented, and this is in the uncomplemented form. So this is the same as m, capital M subscript 0. So this is a max term and this is the 0th max term. Then you have this is 1, 0 and 1. So we have that as 2. Then you have 1, 0, 0, that is 4, and you have 1, 0, 1, that is 5. So x plus y plus z is the 0th max term. This is the max term in the second row, this is the max term in the fourth row, and this is the max term in the fifth row. So f of x y z is pi of 0 to 4 5. So at this point, if you wanted the canonical SOP, it is just sigma of 1, 3, 6 and 7 because those are the terms that are missing here. So let us do one final example before we wrap up. So we want to simplify this expression to the sum of product form. So usually we use sum of products because it is slightly more intuitive to work with sum of products than with product of sum forms. So we will see how to convert this into the sum of product form. This is a slightly more complicated expression. So it has complements on some terms which have a mix of sums and products and so on. This is not just sum of products. So this is a product term, however this is not appearing as a product term. We want to be able to simplify it. So the first thing we can do here is you look at this expression. This is of the form A plus B complement. So we can use De Morgan's theorem and say that is the same as A complement and B complement. So A is this term up to y and B is just z. So this is A complement into B complement. So this is slightly better. However, we still have a complement that is at the top here. So this w bar plus x bar and y, the whole thing is complemented here. Again we can use De Morgan's theorem and say this is A B complement is A complement or B complement. So this is A is w bar plus x bar, let us say, and B is y, then this is A complement or B complement. And again there is still a complement on two terms, so we need to be able to simplify that, and that is w bar plus x bar's complement is same as wx. So now it is slightly better. We do not have these complements running over multiple terms. The complements are actually contained on each. So you have only literals which are complemented, not whole expressions which are complemented. Once you get there, it is a fairly straightforward process. So we have wx plus y bar into z bar plus wxz. We can rewrite that as w plus y bar. So wx plus y bar, we can write it as w plus y bar into x plus y bar into z bar, we already have that, plus wxz. So at this point, from here you can branch off and do something completely different. You may end up with the same result, but here I am trying to reinforce a few ideas here. So if I have something of the form a plus bc, we have a plus b into a plus c. The z bar is actually common to both of them, so that just appears as a term here in the product, plus wxz. Now you expand everything out. So this is wx, wy bar, xy bar, yy bar and so on, and you have the z bar which comes here plus wxz. And if you simplify it, it turns out it's wx plus y bar z bar. So from this point you may be able to jump here directly. It's slightly more involved though. However, this one, so the process that we have is slightly more complicated. Jumping from here to here is actually slightly simple. I suggest that you go and do that. So I have one form of derivation here. You try and take this expression and get here directly if it's possible. So you can take that as one of your exercise problems. So this brings me to the end of this module. I'll see you in module 6.